Hi there, this is exercise 11F, well split into two parts, so we've got 11F.1 here. And I've just gone to the top of the slide here, you've got a couple of graphs which you don't normally see, so it's worth just commenting on initially. Just turn the pen on. So normally, of course, we know that a sine graph looks like this, and it basically does this, doesn't it? This is the sine graph. So I'm interested up here what happens when I square that thing. And it shouldn't surprise you to learn. It only goes up to 1. So it doesn't, 1 squared is 1. So the maximum it can be is still 1. That's why it goes up to 1. But obviously it goes down to -1, the sine graph. So square -1, you get 1 again. And so that's why the 1s appear more often. 0, of course, squared is still 0, and everything else is in between. So I think they're quite nice graphs. Of course, they're very similar graphs as well. One's a reflection of the other. Looks like in the line y equals a half. Anyway, so that's the graphs of these sine squared and cos squared. And the reason I'll comment on those is because we're going to need them today for what we're going to do. State the following. It says sine 2x. Now, here are just a few identities that you're meant to know. And on the right hand side over here, it's a couple of rearrangements I want you to do. So see if you can write all those down for me so that you've got all these things in your book. And if you haven't done so already, I hope you've paused the video and written them down, and I'm now going to write out the answers that you're meant to know. So sine 2x you're meant to know is 2 sine x cos x. This is a standard identity. Now this one, cos 2x, there's actually 3. And the standard one is cos squared minus sine squared. But they can be written in 2 other ways. So there's all 3 ways you're meant to have written down. Hopefully you've written those down. Here they are. Now you can see the cos squared minus sine squared one I've written third. Obviously you can't chuck a couple of x's in it, it's done properly. But these 2 come about because we should know that cos squared x plus sine squared x is equal to 1. And if that is true, that's an identity that we're meant to know off by heart by now. If that is true, I can substitute it in, because you can see I can get cos squared on its own by moving the sine squared over. And that's 1 minus sine squared. So if I chuck it into there, I can get this equation, or I can do it the other way around and get this equation. Now, based on those, you effectively get 2 identities for cos squared and sine squared. And so if on this one, if I just do this one, you'll see what I mean. I get cos 2x. I'm going to move the 1 over. That's my first job. I'm actually going to put it there. 1 plus cos 2x equals 2 cos squared x. So the 1's moved over, comma plus. And you might think it's a bit weird I've written 1 plus at the front, because I could have written it there instead. There was a reason for that. And then I'm going to half it, because I don't want 2 cos squared, I want cos squared. So it won't surprise you to learn that this is a half of 1 plus cos 2x. Now the reason why I put the 1 at the front is because if I do the exactly the same trick for sine squared using this formula, I get half of 1 minus cos 2x. And it's quite nice that these 2 equations are effectively the same, just one's a plus, one's a minus. Can you write these down if you haven't already done so? These are important, these equations. They get used loads in integration, so you want to know them. Now section C is just some integrations you want to know, and these are the answers for them. You can just about see them, but I want to stress to you, this is what the formula book says. The formula book does not tell you what the integrations are. So it does not say to you in the formula, if I integrate x squared, I get tan x plus c. That's not there. But interestingly, what is there is it tells you if I differentiate tan x, I get sec squared. You can ignore the case for now. So therefore, by going backwards is the integration. So this is integration, this is differentiation. So even though they don't tell you everything, it is there in the formula for you to use. And you'll notice all 4 of these are here in some form or another. Cos x squared, for instance, I've written as minus cot x. Interestingly, they've written cot x as minus cos x squared. They put the minuses the other way around. But that's because it's the other way around that we're doing it. So just be aware of those, please, and make sure you've made a note of them. They come up enough times to make it useful if you've learned them. So anyway, show that the integral of tan x is the log of sec x. So I suppose the way to do this, this is a proof. This is a formula you're meant to know. Just realise this has just dropped off the bottom. We'll probably do that forever now. But integral of tan x then. Now you should remember that tan is sine x over cos x dx. And I need to highlight a formula for you, which comes up a bit more again later on. But it's basically the integral of, if I have a fraction and there's some function on the bottom, but the top of it is f dash x. And if I am asked to integrate a function where I've got the fraction is the, if I look at the bottom, I get the differential on the top. And of course, I think this is nearly that. I've said sine cos minus sine minus cos. So if you differentiate cos, you get if you differentiate cos, you get minus sine, because this is differentiation. This is a weird thing about this question. It's an integration question, but in order to do it, I'm having to talk about differentiation, because you'll notice it says f dash on the top. So if I differentiate cos, I get minus sine, and my rule says that I'll get the log of the bottom plus a constant. So this is the log of the bottom, which is the cos plus a constant. But it's not quite true, because I've said you get cos goes to minus sine, and of course mine didn't say that, so I've actually got to throw a minus at the front to take account of that. And that minus at the front is like minus 1 times by the log of cos x. And the minus 1 can go up here as a power, so that becomes like log of cos x to the minus 1. And of course cos of x to the minus 1 is the log of 1 over cos x, and it should now be a reciprocal function that you remember. This is the same as the log of sec x. So that's a lot of work just to prove it, and it would be easy to forget that minus and then not really understand where the sec comes from. The sec comes from the minus being translated to the power, and as a power to the minus 1, that means 1 over cos. So that's the reason why that if you integrate tan x, you get log of sec x. Notice there isn't a tan x here on this list. They don't tell you this formula in the book. So you could almost add it here. You could say, if it's tan x, I will get the log of sec x. And presumably you could be asked to differentiate the log of sec x, and you go, that's tan x. So anyway, 3 functions. Let's have a look at it. So on each one of these I've given a little hint in blue as to how to do them. So hopefully they should mean we don't make any daft mistakes. If I can find my pen, there it is. So integral of tan squared, I've said, look, on the face of it, you can't do it. Nowhere does it say tan squared becomes this. But what it does allow us to do is, if we use this identity that we've seen up till now, it says tan squared plus 1 is sec squared. And tan squared plus 1 is very useful to know, because of course I've got tan squared, so I can just move the 1 over and I get tan squared is the same as sec squared minus 1. So just write that in here. This is the same as the integral of sec squared. Notice that at the moment I haven't integrated. All I've done is rewrite. But that's why we do it though, because sec squared becomes tan when they integrate. Oh, that's interesting as well. You start with tan squared, you rewrite it as sec squared, but when you integrate it, you get back to tan. There's no k's, 2x's, 5x's, so there's no thing to worry about other than tan x. Now if I integrate 1, I get x, so it's minus x plus a constant. Tan x minus x plus c. So the sine squared. Now you will recall as well on the last couple of slides I showed you how to integrate these two things. Well, I hinted at, and I said you integrate using sine squared equals, and I wrote this identity over half of 1 minus a cos 2x. Now this was the way I wrote it, but you can see it's quite easy to say to yourself, well, you can multiply out the brackets and you would get this formula as well. Now you can use either, to be honest. I've written it like this on this slide, so I'm going to carry on using it. So it's the integral of sine squared is best written like this. Basically, you've got to say to yourself, I can't integrate sine squared or cos squared unless I rewrite them. And here is the rewritten version. It's a half minus a half cos 2x. So now I can do that. This is something we've done before. And of course, we've written sine cos minus cos. Just to be clear in your mind, are you integrating or differentiating? If you're differentiating, you go down. If you're integrating, you go up. So what have we got? We're integrating, so we're going to go up. And we've got, well, a negative amount of cos x's. A negative cos goes to a negative sine. So just bear that in mind. A half becomes a half x out of the power. And a negative half cos 2x. Now, it will become a sine 2x. It will stay as a negative, because my rule tells me it does. But it's a half now, but because it's cos 2x, the 2 has to go on the bottom as well. I end up with a quarter plus a constant. Half x minus a quarter of sine 2x plus a constant, which is right. This last one is a bit weird. I'm going to use a substitution, which we come up to properly in chapter 10. For that reason, it's probably worth me saving this to actually when we're in class, because although it's useful, it's not probably something that's best done via video. So this will probably tell me what the answer is. There's what the answer is meant to be, but we'll worry about that next time. For now, just be aware that we're going to have a look at some questions on exercise 11F, and as I've already said, this is done in 2 parts, so I'm only suggesting a couple of questions. Notice please I've written in there the integration of tan is log sec, and all these differentiations, but I've already said you have to know that you're working backwards. So hopefully all that helps, and we'll have a look at exercise 11F again in the next lesson video.